Hey guys, hope you're all doing amazing and welcome back to another video. Today we'll be looking at how to handle missing values, create data visualizations, and conduct hypothesis tests. We will be mainly using Excel to conduct our analysis, but I'll also be doing some handwritten calculations. To make this video more interesting, we'll be looking at a real-world dataset for Sydney's rainfall. The rainfall has been a hot topic. Well, that's a bit contradicting. Anyways, in recent months we've experienced large amounts of rain, with 2025 being one of the wettest years on record, and we're only in September. We have seen flash floodings that have caused a lot of disruption, like closed roads and public transport delays. I'm just looking forward to the summer so we can finally get some outdoor time rather than being confined to our homes. Okay, let's get into the first part of this video. So here I've already imported the dataset we'll be working with, which looks at the monthly rainfall in Sydney between 1885 and 2024, which I got from the Australian Bureau of Meteorology. Now, if we scroll down, you may notice some blank cells. Well, when I imported the dataset, there was missing data. So, what is the best way to deal with this? Well, we don't want to delete columns or rows because we don't want to lose information. So what I think is the best is to calculate the average for each month and use that to fill in the missing cells for their respective month. To do this, we can just calculate the average using the average function. So first, we'll just type in average to have a description of what we're looking at. And we can use the Excel average function by simply typing in equals average. And now we just got to select our cell range. So we'll look at January, scroll all the way down, do that, press enter. And now we've got our average rainfall for January across 1885 and 2024. Now, to make it easier, we can actually just drag this bottom right corner of this cell across all the way to December. And this gives us our average for each month. How easy is that? Now all we have to do is copy the values for each month within their respective cells. So we can do here, 97.6 for January, 97.6 for January. It's as simple as that. Now, before starting this video, I already prepared a clean dataset. As you can see, I've already entered in those values. Now on the right, we have our annual total. And we can calculate that by using the sum function. So first, all you'll do is type in equals, and that's sum. We're just going to select our cell range from January to December. Got that, hit enter, and we've got our annual total for 1999. Now we're just going to drag down to fill in the rest of these empty cells. And now they're all filled up. And we can move on to the next part of our analysis. Okay, so for the next part of this video, given that our dataset is so large, we're going to take a smaller sample subset, focusing on the rainfall between 2010 and 2024, which reflects more of the recent rain we have experienced. This will also be quite important for the latter stages of this video, where we will be looking at hypothesis testing. But for now, let's copy our data between 2010 and 2024 and copy it into a new worksheet. As you can see, I've already created a column labels. I'm going to copy it over here. Okay, now what we're going to do is make some data visualizations so we can get a better understanding of those wet and dry periods on a yearly basis. The first way we can do this is through a heat map, which uses a lot more coloring to give us that visual cue. In Excel, what we can do is highlight the data that's going to be affected, which is January to December rainfall. We're going to hover over to conditional formatting. Let's click on that. What we're going to go to is color scales. I'm going to select this option right here. And boom, now we can see our heat map. And straight away, we can notice that those periods between August to December are a lot more green and yellow, indicating less rain. And then when we go to February to June, we can see a lot more orange and red patches, indicating slightly more rain. So if you have any family or friends overseas that want to come visit Sydney, tell them to come between August and December to experience that sunny weather. Another way we can visualize our monthly rainfall is with a simple bar graph, which provides better readability for making comparisons. First, what we're going to want to do is select the column labels we added earlier. Copy that here, and let's go down to like row 20 and paste it here. Now what we're going to want to do is calculate the average rainfall for each month between 2010 and 2024. First, for our own reference, let's just type in average so we know what we're looking at. What we're going to do is go over to this January cell, type in equals, and we're going to recall the average function we used earlier. So let's type in average, open bracket. Now we want to select our cell range for the January data. Let's do that. hit enter. What we're going to do is select that cell again. We're going to drag across all the way to December. And for better readability, we may also want to change this general format to a number format, less decimal places. And now we have our average monthly rainfall between 2010 to 2024. Now to create our bar graph, what we want to do is select these values here, go to Insert, select Recommended Charts. Here we can see a clustered column chart. This is what we're looking for. Let's select that. Let's bring that down a little, make it a little bigger. And for better readability, we might want to reduce the gap width. So what we want to do is double click on one of these columns. Then we're going to go over to the right here on Format Data Series. See Series Options. Let's select that. Now we can see gap width. Let's say we want a gap width of about 5%. So enter. And now we have our average monthly rainfall bar graph. And as we can see, February, March, April, and June experienced the most rain in the last 15 years. And from July to December, majority of the rainfall is under 100 millimeters. So now that we've got our visualizations, we can rename the worksheet to something more appropriate. Let's just call it Visualizations. Now we can move on to the final part of the video, hypothesis testing. Okay, so what I'm first going to do is some handwritten calculations for our hypothesis test to give you a better understanding of how we reach our conclusion. Now, as you can see, we have our research question. Has Sydney's annual rainfall changed significantly in the past 2 decades? We also have some key details. So I've already calculated the mean annual rainfall of our population data, which we saw earlier, and this is 1,220.4 millimeters. I've also determined an alpha, or significance level, which is 0.05, and this basically represents our false positive rate, which is the chance of us incorrectly rejecting a true null hypothesis. So now what we want to do is determine our null and alternative hypotheses. So first, our null hypotheses, denoted by H0, and this is going to be equal to 1,220.4. So this means that there will be no significant change in annual rainfall over the past 2 decades. Now, our alternative hypotheses, HA, is going to be that there is significant change in annual rainfall in the past 2 decades. So we're going to say this does not equal to 1,220.4. Okay, so now what we want to do is calculate our sample mean, which is why I've included the sample data we saw earlier, but only looking at the annual totals between 2010 and 2024. So, to calculate our sample mean, denoted by X bar, we want to sum up the totals for each year. So we'll start with 1,399.9, and we want to add 1,402.9, and we'll just do a little ... here, so we don't have to write these all out. We'll just add the last value, 1427.7, and we want to divide this by our sample size, which is the total number of observations in this data set, which would be 15. Divide by 15, and this should give us a sample mean of 1,343.6. So now we're going to conduct a t-test to see how significant the change in rainfall has really been by comparing our population and sample means. But before doing this, we need to find our t-critical value. Now, the critical value is difficult to calculate by hand, so I'll be using the student's t-table for two-tailed tests, since we're only looking for change and not a specific increase or decrease. You can find the link to this table in the description below. Now, as I mentioned before, our significance level is 0.05, which will give us a t-critical value that is approximately equal to plus or minus 2.145. Okay, now we want to calculate our t-statistic using the t-test formula, which is t equals to x bar, our sample mean, minus mu naught, our population mean, over the sample standard deviation s, divided by the square root of n, our sample size. Now, we know x bar, the sample mean, equals to 1,343.6, and we know the population mean, mu naught, is equal to 1,220.4. And I've already went ahead and calculated our sample standard deviation, which is equal to 255.3, and n, our sample size, is equal to 15. Now, if we put these into the formula, it's going to be 1343.6 minus 1220.4 over 255.3 divided by the square root of 15. And this should give us a t-statistic of approximately 1.87. Okay, now let's draw a normal distribution where our t-critical value will specify the rejection regions. So if we scroll down a little bit, we can draw a line. And now what we want to do is draw a normal distribution. There we go. And now we know our significance level is 0.05. So this will be split in half to cover both ends of the tail. So we've got 0.025, 0.025. I'm just going to color these regions in a little bit. Same with over here, we'll color it in. Now, we know our t-critical value is 2.145, as we saw here. So on the left-hand side, negative 2.145. Here we're going to have 2.145. Say this is our center. And we know that our t-statistic is a 1.87. So that roughly falls in about here. So 1.87. So what does this mean? Well, our t-statistic, our t-stat, is less than the t-critical. And that means that we fail to reject the null hypothesis because 1.87 does not fall within the rejection regions. So therefore, we can say we fail to reject the null hypothesis. So with the significance level of 0.05, we can say there is not enough evidence to suggest Sydney's annual rainfall has significantly changed from 1,220.4 millimeters over the past 2 decades, and that's that. So, we are going to use Excel to conduct our hypothesis test on if Sydney's annual rainfall has significantly changed. Now you can see I've got our population and sample datasets, which will be needed for the data analysis tool we are using, known as the t-test, to sample assuming unequal variances. And the great thing about this is we don't need to make any calculations, just select our data ranges. How good is that? Okay, what we need to do is select data. We see this data analysis option on the right. Let's click that. And we're interested in the t-test to sample assuming unequal variances. Let's double click on that. Right, so our variable range 1 will be our sample data. Highlight that. Our variable range 2 will be our population data. Let's highlight all of that. And we're going to leave this one here blank. And we do have labels, so we're going to leave that checked. And our alpha or significance level is 0.05, as we previously stated. And our output range, let's select somewhere over here. Okay, and let's click OK. And let's expand these columns. Okay, what we're interested in is our t-statistic over here, so we'll highlight that. Also interested in the t-critical two-tail, and we're going to highlight that. And we're also interested in this p, our p-value. Okay, so an important thing to note is that the values calculated by Excel for t-statistic and t-critical are slightly different to what we had when we hand calculated them. This is because Excel has its own conventions and formulas for working these values out. So the point of the fact is this isn't too big of a deal because we still reach the same outcome. So if we look, we've got a t-statistic of about 1.7, and our t-critical for two-tail is 2.08. So our t-statistic is still less than the t-critical, which means that we failed to reject the null hypothesis. And the same thing we can do is talk about a p-value. So when the p-value is greater than our significance level, which is 0.05, we failed to reject the null hypothesis. And there we go. We've calculated and done a hypothesis test on Excel. So over 15 years of data, Sydney's rainfall has shown strong seasonal patterns, but no statistically significant long-term increases or decreases. Whether future years bring more droughts or downpours, hypothesis tests and data visualizations will remain vital for understanding and adapting to our changing environment. If this video gave you the help you were looking for, hit that like and subscribe button, and if you have any questions, please comment down below. Thanks for tuning in, and I'll see you next time.